This computer, and the computer has an invisible side that's only visible to the operator of the computer. And then when he sends something out via email, it's visible, of course, to the whole world that can intercept emails, which is everybody now. So he's working on his invisible part, and he decides on the message that he wants to send is a simple word, hello. So he moves it over to his visible part, where it's transmitted across to the receiver. So the receiver picks it up on his email and moves it to his internal private space and reads the message hello, and the transmission was totally successful. Absolutely no problems. The only real disadvantage is that along the way there was a bad guy. And he also picked up the message hello. And that's something that you didn't want to happen. So you say, well, that's no real problem. What's the problem with this guy picking up a message that's saying hello? And you say, that's no problem at all. But there's a possibility I could have been sending some data that was much more sensitive, in which case I would not have wanted him to pick it up. For example, suppose I was sending a message that would have completely revealed my identity to anybody that was interested in identity theft. For example, suppose I was sending my favorite color. I would certainly want to have that encrypted. So I'm going to take as my favorite color, violet. This isn't actually my favorite color. You didn't actually think I would tell you my favorite color, did you? And before I send this, I realized from my experience with hello that I have to encrypt it. So in order to encrypt the message, you need two, an encryption scheme. And the encryption scheme I've chosen is one of the simplest ones that's ever exists. It's called alphabet forward. I created it 2 weeks ago. Nothing to be simple. I'm sure it exists already. And in order to use it, you need to have a key. So besides the message that we want to encrypt, we need to develop a key. Now the key that I've chosen is the 2-digit key 65. And the way that I use this key, my structure, is I write it under the entire letter, message, and I repeat it until I come to the end of the message. Now in actuality, my message will be a huge document with thousands and thousands of words in it. And in actuality, my key will be a 50-digit number, not a 2-digit number. Would you prefer me to use the 50-digit number? Well, thank you. So I'll go along with a sample 2-digit code. Now the way that alphabet forward works is that I take the letter in the alphabet and I forward it that many. So to make life easy and to save myself and you from embarrassment, I put the alphabet on the board. And we can take the letter B and we just advance it 6 places. 1, 2, 3, 4, and we loop sometimes. So we go to the end of the start of the next alphabet and we come to A. So this letter gets encoded as an A. And quite similarly, the letter I, if we advance it 5 places, 1, 2, 3, 4, 5, becomes N. So this alphabet forwarding enables me to produce encoded word, and the O becomes a U, the L becomes a Q, the E becomes a K, and the T becomes a Y. So now I forward my encoded word to my visible section, and I send it, and it's received by my receiver, who receives it and then moves it into his private section. So he also has now A-N U-Q-K-Y. And of course the bad guy picks it up. Now we don't worry about this because it's totally indecipherable, agreed? Because we've encrypted it. So we feel really smug, safe, and secure until we get a message back from our receiver that says, that's your favorite color. I can't make any sense of it at all. And you say, of course you can't, because I encrypted it. Well, would you mind sending me your encryption key so I can decrypt it? So he says, not at all. So we send over the 65 that we used to encrypt it. It comes over to him, and he puts the 65, because he knows it's alphabet forward, we share that, and he goes backwards. When we went to the right of the alphabet, he just comes back to the left. and he produces violet. And he says, wow, it worked. Violet's your favorite color. But I can't remain friends with someone that has a favorite color of violet. Relationship over. So it worked, but it didn't work. So the bad news, of course, is that the bad guy now also knows that your key is 65. And because he knows that your key is 65, he can also reverse the encoding. And he also gets the violet. So it didn't work to send your key straight forward. So the next step in sophistication is that not only have you encrypted the message by using a key, but now you have to also encrypt your key to keep the bad guy from picking up the key, being able to decrypt your message. So you need a scheme for encrypting your key. Now a very simple scheme is called 9's complement. You take your key and you subtract it from a string of 9's. And it's called 9's complement. So what would your encrypted key be now? 34. So lo and behold, you read 34 out to your public area, and you send it across to your friend, and he receives the 34, and he says, thank you very much for the 34, and he moves the 34 in, and he tries to decrypt using it, and he produces nonsense, because he didn't know the scheme by which you encrypted it was 9's complement. So he's still missing that information. And of course, the bad guy picked up the 34, and he also can't make any use of it, because he doesn't know how you arrived at the 34. What was the algorithm that came in the 34? So your friend goes back to you, what was your algorithm that you used? I need to know to encode your key. So you very quickly tell him, well, I used the 9's complement. Oh, you use the 9's complement. Well, 9's complement is reversible. Very easily reversible. If you start with the 65, and you do a 9's complement, you get the 34. But if you take the 34, and just do a second 9's complement, you get back to the original. So the 9's complement is totally reversible. So as soon as it's known that you produced your encryption key by a method of 9's complement, then not only can your receiver decrypt your encrypted key and get back the original key and use that in the message, but so can the bad guy. So this is a head-scratching point that we're in 1977. You remember it? I remember it. When we had this process that no matter what we did to the key, we had to communicate to the receiver what we did to the key. The bad guy can pick it up, and he can do the same thing the receiver could. So everybody is stuck, because what we needed was a method of encrypting the key that is not reversible. Let's take some of the common reversible operations that we can do on the key. Suppose the key is designated by X. If we hide the key by multiplying by 3, so this becomes our encrypted key, cannot that be reversed by dividing by 3? So the operation of multiplication is easily reversible. If we hide our key by adding 3 to it, can that be reversed by subtracting 3 from it? So we need an operation that we can do to our key that is not reversible. So enter now the operation called modulus. Which is not reversible. Therefore, it's entirely suitable to use for a key that you do not want the bad guy to be able to reverse. So I'll give you examples of what we mean by modulus. 27 modulus 5 equals 2. 13 modulus 2 equals 1. 11 modulus 3 equals 2. Those of you that have either seen this before or fairly quick realize that what I'm talking about is the remainder. Modulus is the remainder that's generated. If you divide 27 by 5, the remainder is 2. So 27 modulus 5 is 2. If you divide 13 by 2, the remainder is a 1. So let's try one of these hard ones. 27 divided by 5 goes 25 times, and lo and behold, the remainder is 2. So this 2 is the modulus. 27 modulus 5. So let's see if you can do one or two of these. 39 modulus 6 is what?
3.
3. Okay, good. Now this has been abbreviated as 39 mod 6 instead of the word modulus. Now I've never approved of the word mod. And those of you who know me well can understand why. And those of you who know me well also understand that my opinion was never asked for. So they went ahead with mod. Simple mods we don't have any real hard to do. So please tell me, what is 1312 mod 211? I can do it. Because most calculators, at least the one I'm using right now, with a mod key. And you can identify the mod key because it has MOD on it. So let's make use of this mod key.
46. 46. I think it's my calculator.
Well, it's 46. As I told you, I had a calculator on this side of the room.
211 times 6 equals 1266. The range is 46.
Okay, so 432, what does that say?
9672.
9672. And I press the mod key, and I want the modulus of
1392.
Okay, 552, that's what you got, right? So you can make use of the mod key on your calculator, or you can ask a bright student to generate certain modules for you that you might not be able to do yourself. Let's check them on this one. 1312 mod 211. You maintain your 46, right? And he's totally confident.
You need to read. You need to clear. You need to clear it.
1312 mod 211.
You need to clear the calculator.
What's the next section? 1312 mod 211 equals. And I have to put up with them twice a week for 7 weeks. Okay, as he says, it's 46. So now we understand what mod means, and you see, for a reason that I'm about to indicate, that mod is a perfect way to hide our key. Because if I give you the following information, first let's look at some series of numbers. So 7 mod 5 equals 2. 12 mod 5 equals 2. 17 mod 5 equals 2, etc., etc., etc. 97 mod 5 equals 2. How many numbers have a modulus of 2? An infinite number of numbers. If you mod 5, you'll get a 2 as mod 5 to that number. There's some infinite number set of numbers. So if I take my key and I hide it in the following way. I take my key and I say that my key mod 5 equals 2. I've certainly hidden my key, agree? Because the bad guy picks this up because you send it, that the key mod 5 equals 2. From this information, can he go backwards and get the key? Because how many possibilities are there?
Infinite.
Infinite number. So he cannot go backwards, can he? So as soon as I hide my key by taking a modulus with some base number, it becomes irreversible. And that's the secret of public key encryption. That we hide our number by taking its modulus with some base number, such as 5 in this case, and as soon as we do that, it could be any one of an infinite set of numbers. And the bad guy cannot decipher it in the slightest way. So that's exactly the solution. The goal is, as you can see ahead, is that as soon as he gets over here, this guy has exactly the same problem. That all he knows is that the key mod 5 is equal to 2. And he can solve that equation, then he could go backwards into your encryption. But he has exactly the same problem as the bad guy. This is an infinite number of possibilities. So the solution to the problem is that before you send out your key and take the modulus, you raise it to a certain exponent. Now this little e is called an exponent. I'll give you an example. 3 to the exponent 2 is a 9, so the 2 is called an exponent. So we're going to create some exponent that if you raise your key to this exponent and take its modulus, then the number that comes over here is going to be your encrypted key. Your encrypted key becomes a 2. This is how you encrypt it. You start with your key, you raise it to this power, you take the modulus, and this becomes your encrypted key. And now the bad guy is even worse off than he was a moment ago, because he could not tell what your key was just by knowing the mod 5 was 2. Now if you raised your key to some power before you took the modulus, now his job is even harder. He can't figure out what it was. The reason it improves the abilities of the receiver is that this exponent was very carefully chosen by the receiver. He chose it in just such a fashion that he has a magic number. And only he has it. He has a private exponent called D. And if he takes your public exponent, your encrypted exponent, in this case 2, and he raises it to the power D and does another modulus, then he's going to get back your original key. I'll give you an actual numeric example. Let's take this key 65 that you want to encrypt with this modulus technique. The process starts not with you, but with the receiver. The receiver chooses what modulus will be used. He makes that choice. The receiver, before any message is sent to him, he creates his public modulus and broadcasts it to the whole world. And in this case, we're going to create a 3233 as our public modulus. We're going to send it to the whole world. Next, he creates a public exponent, which he's also going to send to the whole world. In this case, he creates the public exponent 17. This is now visible to everybody. Everybody knows if you want to send him an encrypted key, you use the exponent 17, and you use the modulus 3233. That's the rules of the game. So let's apply that to our 65 and encrypt it. So to encrypt 65, we take the 65, which is our real key, and we raise it to the public exponent. What's his public exponent?
17.
17. Then after we do that, we take the modulus of the public modulus. What's the public modulus?
3233.
3233. And this becomes our encrypted key. So, Jose, what's our encrypted key going to be? Okay, let's do it on the Windows calculator. So the first thing that we have to do is take our real key, 65, and we're the only ones that know the real key. It's invisible. We take our real key, 65, and we raise it to the power of 17. And we see what number that produces. A relatively small number. Now this is the reason that even though the bad guy knows exactly what you're doing, he knows that you are taking your key, which he doesn't know. He knows you're taking it to the 17th power because that's public. And he knows that you're then taking modulus of 3233 because that's public also. And the reason that he cannot work backwards is because that number is so big that if he tried to guess what your key was by all the possibilities of that number, it would be 10 to the 211th power years, which you're willing to wait for. So you're safe by numbers in this case. So let's finish the encryption. You've taken 65 to the 17th power, so what's the next step?
Mod
Mod what?
3233.
3233. Mod 3233 is 2790. 2790 becomes your encrypted key. So you send it out as a 2790. So your encrypted key is known to be 2790. And you send it out, 2790. So this is what you broadcast. You broadcast your encoded message, and the key is 2790. The bad guy picks it up, and he knows that how you got to 2790 was by this equation. But can he work that equation backwards? It's a modulus equation. It has no backwards. So he can't go backwards. So the only thing he can do is try to guess your key one number at a time and see if it fits this equation. Which he can do in 30, 40 years with a very fast computer. So you're not worried about that. Because in actuality, your key is 50 digits long. And because your key is 50 digits long, then by sheer guessing, he cannot guess it in a practical amount of time. The only thing he can do is reverse his equation, but modulus equations are irreversible. So he loses. Now the only thing left is how does your good guy win? Because your good guy has a magic number. He has this magic number. D equals 2753. I'm going to show you in a couple of minutes how he created that magic number. But because he is the only person in the universe that has this number, he is the only person that can work that equation backwards. If you don't have this number, you can't work that equation backwards. If you do have this number, you can work that equation backwards. So this is a secret number, very private. Everything on this side of the line stays home. Let's see what happens if he takes the key that you sent him, which was 2790, raises it to his private exponent, 2753, and then one more time takes the modulus of 3233. Well, that's a fairly large power. Let's see if this computer can handle it. I haven't tried yet. 2790 going to take it to the power of 2753 and see if we can multiply it. And it did multiply it. Notice the exponent. It's only 10 to the 9,485th power. So good luck for the bad guy trying to count up possibilities, true? We're not worried about that. But now let's look at the magic that happens if I take a modulus 3233. Modulus 3233. Bingo. End of magic. Original key recovered, true? And untouchable by the bad guys. So the original key is recovered, and the bad guy couldn't have done it without this gadget number key. So with the original key in place, I can change this back to violet. So the key 65 has been transferred to the receiver. Key 65 has been taken to a public exponent, is modulated by the public modulus, which creates an encrypted key. The encrypted key is transmitted safely.
Thank you.
Thank you.
Thanks, buddy.
It's pretty easy.
This? Great. Terrific. You're going to be captain of one of the teams.
Oh, man.
We're
Well,
going to
I
have
took,
sitting and receiving teams, and you're going to be one of the captains.
all
You
right,
just volunteered.
I'll take it.
You got it.
I took lots of detailed notes, so I'm pretty confident.
Me too. Pardon?
I'm really sorry for what's happened.
That's okay. We did chapter 7, and chapter 8 is assigned for next class. And we also want you to watch this movie. I sent you an email. And we also want you to bring in your Access project finished. That's the story. Now, if you watch this video for tonight's class, then you have enough to do without the new things. So just bring in your Access project with all the things you already know about. Okay?
Okay.
Okay, see you then.
Yes.
Okay, bye. You too. So how's it going? The language is a trouble?
Yeah, it's like,
The language is a trouble.
yeah.
But on Wednesday, we will do this in class. So you, just what we're doing.
Oh, okay.
So you will not be able to learn it when we do it. So you don't have to learn it by the movie.
Okay.
It's okay.
Until that, like, mathematics part,
Yeah.
I kind of, could follow, like,
Well, you should
What?
take Math 103, then you would know how to do that math part. Really, yeah, you should do
is
that.
this covered?
Yeah, because, you would learn that there, how to do that stuff.
Okay, well,
Yeah, I'm not worried about you, I know you're both doing fine.
yeah,
Okay.
I really feel thanks to the whoever invented the computer.
Well,
Because-
keep your private opinion,
Yes.
I know.
Can't do that.
Okay, okay.
Okay, thank you.
Good night.